In section 10.2, junction field effect transistors, sometimes they're referred to as a JFET, from J-F-E-T. FETs are another class of electronic components. FETs are similar to bipolar transistors in that they can be used as amplifiers and switches. Notice they mentioned they are similar to bipolar because these represent a group that are called unipolar, and we will talk about why in a few minutes. Field effect transistors are also very unique in their construction and operation when compared to bipolar transistors. Okay, FET construction. JFETs are constructed from P and N-type materials, but in a very different way than bipolar transistors. A substrate of P material has a pocket of N-type material diffused into it. So you start with a piece of P-type material, N-type material is diffused into it, and then another piece of P material is diffused into the N-type material. So you have a configuration looks kind of like this. Wires are connected to form a source, so a wire would be connected here, here, and to these 2 points here, making the gate. Now in this case, the current flows through N material only. So current is going to flow from the source to the drain, and it is flowing only through N-type material, in this case with an N-type FET. And hence the term unipolar, because the current is only going through one type of material. Okay, the FET just described was an N-channel FET. P-channel FETs are constructed in the same fashion, except the material type positions are reversed. Current flows through the channel between the source and the drain. So remember we had our transistor configuration. We said that current flowed basically from emitter to collector, and this is a schematic symbol for a FET, and again current is going to flow in this, but not emitter to collector. It will be source to drain. And then here we have the gate, and again we have the arrow, and this line right here indicates the channel, and this is the channel that current flows through from source to drain. This is actually the gate in this little circle right here. And then this would be a P-type channel, and again the arrow was pointing at the N material of the gate, and that would indicate that the P channel here is in the channel in that case. And current flows from the channel between the source and the drain. Biasing for N-channel FETs is shown at the right. Okay, so here we have our biasing. You'll note, let's see, we have some voltages applied to this. Notice we have VDD. This would be for the voltage on the drain. And you'll notice there's a negative voltage connected to the N material here, and the positive is the other side of the N material, and so current would flow through the N material as such, and this would define the current in the drain. Then we have another voltage that's applied, and this voltage is between the gate and the channel. Notice that we have a positive here going to the N material and a negative going to the P. Now this is a reverse bias configuration. This is reverse bias here. Notice we're showing 1 volt here. We're going to show increasing values of voltage here on screens that will follow after here. The two parallel PN junctions are reverse biased, causing a depletion region to form in the channel. Note positive N and negative on P, and we pointed that already. So since they have a reverse bias between the P and the N, we're going to have a depletion region at the borders of the P and the N material. Now this is a low voltage now, is at 1 volt, and we do have a depletion region, but it isn't very large. Increased reverse biasing causes the depletion region to expand, increasing the resistance. So as we increase the values of voltage here, we're going to increase the depletion regions, and hence we're going to increase the resistance of the N channel. In this case, the VGG value is 1 volt. It is common for this value to be 0 for max current flow, and hence there would be no reverse bias. So if this was at 0 volts, you would have maximum current flowing from source to drain. Now this is just opposite the way that a bipolar transistor would work. If you had 0 volts on the base of a bipolar transistor, you would have no current flow. But with a FET, 0 volts on the equivalent gate would make for maximum flow of current. Okay, as the value of reverse bias from VGG increases, note that the depletion region increases and begins to choke the flow of current through the N material. Now it was 1 volt on the previous screen, now it is 3 volts, and you'll notice that the depletion region here is becoming larger, and it's beginning to, electrons want to go from here over to here, but they are literally being choked, and we're experiencing increasing resistance in the channel and decreasing flow of current through it. The behavior of the N channel is much like a resistor. With low reverse bias, it has very little resistance to current flow. With increases in reverse bias, the resistance increases. And so here, now we're at 3 volts of reverse bias. When a high voltage of reverse voltage is placed across the P channel, the N channel is, and here is an interesting term, pinched off. And so here we have 6 volts here. Now the depletion regions have gotten so large that they have completely pinched off all flow, and current flow through this device will cease. This is equivalent to cutoff in a bipolar transistor. And of note, the N channel has no specific kind of doping that differentiates between the drain and the source. In a bipolar transistor, there was a differing doping on the emitter and the collector, but in this case there is no differing. And so in most FETs, the drain and the source are interchangeable. Bipolar requires forward bias p-n junction for conduction. JFET requires 0 volts, and we had mentioned that before. Okay, so this is our beginning point with FETs, and we looked at the biasing and just a little bit about the construction of these devices.